This lecture is about Newton's second law of motion, which starts with the concept of momentum. And a lot of people think that F equal to ma is the correct formulation of Newton's second law. But does it apply if the mass is variable, like in the case of a rocket? No. The correct formulation of Newton's second law is what you're going to learn right now. A lot of people I know just don't know how to formulate it and how to apply it to a given problem, and their mind goes spinning. But here, I'm going to give you absolutely crystal clear understanding of this law and how to apply it. Welcome to the portals of real learning. Don't skip and listen carefully right till the end. In the last lecture, we learnt about Newton's first law, and that also led us to the definition of force. Now let us learn the second law, which is actually the most important law. In fact, it is the primary law. And as I said earlier, Newton's laws of motion, they are the fundamentals of all mechanics. Therefore, the second law of motion is the fundamental of all mechanics. Before that, let's get on to the concept of momentum. Suppose there are two guys running on a track. The red guy is fat, the blue guy is a little bit thinner, but both of them have got nearly the same speed. Who do you think is harder to stop? Harder means you have to apply a greater force to stop. Who do you think is harder to stop? The fat guy or the thin guy? They both have the same speeds. Well, the fat guy is harder. Mass has got something to do with the force that is required to stop. Take example of this runner, Usain Bolt. He runs very fast. And suppose I were to ask you that you have to stop Usain Bolt. When is he harder to stop? When he is running at full speed or when he is simply walking? It is harder to stop him when he is running. That means the velocity has got something to do with the required force. Third example, suppose there's a building on fire and the guy has no other way but to jump from the window. It is all full of smoke, so you just have to jump out of the window. On one side is concrete. If he jumps onto the concrete, he is going to break his leg. On the other side, there is a heap of sand. If he jumps onto the sand, he probably does not break his leg. What's the difference? Same person, so mass is the same speed on landing. What is the difference now? The difference is while the concrete floor does not yield, the sand does. Yield means allows the foot of the person to come into the sand, to go into the sand a little bit. That means the time that is given to the person to stop is a little bit more than the time that the floor gives. And the time has got something to do with it. Putting it all together, greater the mass, greater the velocity, greater the force required to stop a person, stop a body. And greater the time available to stop, lesser is the force. So that means force is proportional to mass into velocity and inversely proportional to the time. And this product, mass into velocity, is called linear momentum, which is written as P is a vector. Linear momentum is a vector, force is a vector, and linear momentum is P is mass into velocity. So the direction of the momentum is also the same as the direction of the velocity of the body. Larger the mass or larger the velocity, that means larger the momentum. Larger the momentum of a body, harder it is for us to stop it. Okay? And of course, time comes into picture also. Larger the time available to us, lesser is the force required to stop. Now, in order to stop a motion, the force that is required to stop is directly proportional to the momentum of the body. We just saw that. Greater the momentum, greater the force required to stop. And the force required is inversely proportional to the time taken to do so. This holds for linear motion. In the case of rotational motion, look at this wheel that is rotating. We still need to apply a force, but it is not just the force. We need something called the moment of the force, or it is called also torque. We need a moment of the force. Now, moment at a very basic level, moment of a force is the force multiplied by the distance of the line of action of the force from the point about which it can rotate. So suppose I have a rod like this, which is hinged at this point, so it can rotate about this point. The rod has a length L. If I apply a force like this, F like this, then it will rotate clockwise about this point. The moment or torque, which is written as tau, is the force multiplied by the distance of the line of action. The line of action of the force is this perpendicular distance from the point about which it can rotate. That is a moment. Now, to stop this, if I apply a force like this, it is rotating about the center, then there's a torque, the force multiplied by this distance, there is a torque which is anti-clockwise, which will succeed in stopping. But if I apply a force like this one, it is passing through that point about which rotation is going on. So the torque of this force is zero. Although there's a force, there is no moment of the force. And this force cannot stop the wheel. So in the case of rotational motion, we replace force with torque. And we replace linear momentum with angular momentum. The torque or couple that is required to stop a rotating body. What is the torque that is required to stop a rotating body is directly proportional to the angular momentum about the same point about which it is rotating and inversely proportional to the time taken to do so. So Newton's second law then becomes the force that is required to stop a body is directly proportional to the momentum and inversely proportional to the time available or required to do so. Second law states that the rate of change of momentum of the body, that is, change in momentum delta p by delta t, is directly proportional to the applied force. Force is proportional to momentum by time, right? So change in momentum divided by the change in time, force is proportional to that. And the change in momentum takes place along the direction in which the force is acting. So suppose the body has a momentum and there's another force acting on it, then there'll be a change in the momentum, and the change momentum vector will be along the force acting on it. The change momentum vector, not the initial momentum vector, not the final momentum vector, the change momentum vector will be pointing along the direction of the applied force. So Newton's second law, let us develop it now. Force is proportional to delta P by delta T. P is mv, so I'll write delta mv by delta T. Now mass into velocity. There are two variables. Mass can change also. Mass can also change. It is not that mass has to remain constant. And for various reasons, mass can change. We'll talk about that. So if there are two variables and you want to know the change in the product of the variables, then the formula is first variable into the change of the second, that is m delta v, plus the second variable into the change in the first. And delta t is there in the denominator. So m delta v by delta t plus v delta m by delta t, that is the force proportional to that. And actually this proportionality constant that is involved here, choosing appropriate SI units, it turns out to be 1. So force then becomes equal to the rate of change of momentum. In a case when the mass is constant, then mass constant means no change in mass, obviously. No change in mass means delta m is 0. Delta m 0 means the second term will vanish. Delta m is 0. And then we are only left with the first term m delta v by delta t, which as we know is acceleration. So second law boils down to F equal to ma. However, second law strictly is this, that the rate of change of momentum of a body is directly proportional to the applied force, and the change in the momentum takes place along the direction of the applied force. In other words, F is equal to delta P by delta T. Full stop. That is second law. F equal to delta P by delta T. In a special case, if the mass is constant, then the force is equal to mass into acceleration. Now, suppose the mass is constant. If you have a very small mass, then to cause a certain acceleration on that small mass, you need a small force, m into a. M is small, a is given. A is some given number, say 2 meter per second square. If the mass is small, then you need to apply a small force. If the mass is large, you need to apply a large force. That points us to the fact that larger the mass, harder it is for us to make it move or make it accelerate. That means it has got more inertia. Mass is a measure of inertia. Now, F equal to ma can be applied is a vector equation. F is a vector, A is a vector. This equation can be applied along any direction, along x, y, z, or for that matter, along any direction. So, for example, if we have the x component of the acceleration ax and we have the x component of the force, which is fx, then fx is equal to max. Similarly, fy equal to may and fz equal to maz. You can apply this separately along any direction. And therefore, we can say that while we start with saying that mass is the quantity of matter contained in the body, but now we see it is not merely that much. It is that characteristic that determines what the acceleration will be under the action of a force. Mass is that characteristic of a body which decides or determines how much acceleration it will have when a certain force is applied on it. It is not just limited to the concept of quantity of matter inside it. Okay, guys? Very interesting, isn't it? Let us take the case when mass is not constant. One example I can give you when the mass is not constant is a rocket that is going in space. It is ejecting gases, and that is the reason why it is thrust forward. It has to eject gases at a high speed. If it is ejecting gases, it is losing some mass. The mass is not constant. Then F equal to ma won't apply. Then the standard thing that F equal to delta mv by delta t will apply. That is m delta v by delta t plus v delta m by delta t. Both the terms have to be now taken into consideration. That is one example of mass not being constant. The second case of mass not being constant is, as per the theory of relativity, Einstein's theory of relativity, it says that mass changes with speed. Now, you don't observe that in real life, that suppose a thin guy is running, he suddenly becomes fat. You don't see that. The reason is the speed is very small. This thing, it becomes prominent when the speed with which the mass is traveling, it becomes comparable to the speed of light. Okay, not even comparable, even 10% of the speed of light, if it becomes, then the increase in the mass becomes prominent. Otherwise, no. And what is 10% of the speed of light? Well, speed of light is 3 lakh kilometers per second. 10% is 30,000 kilometers per second. 30,000. That means going all the way from Bangalore to New York and back in 1 second. No aircraft can do that, right? No spacecraft can do that. So nothing moves with that kind of a speed. So this is just a theory. We have a concept, therefore, of rest mass versus relativistic mass. Rest mass is the mass of the body when it is at rest, call it m naught. And suppose it is going at a speed v, then this m is the relativistic mass, that is equal to rest mass divided by square root of 1 minus v square by c square. Now you see what happens. Suppose v is very small compared to c, then v by c is a very small number compared to 1. And square of that becomes even smaller compared to 1, and therefore it becomes negligible, and then m is equal to m naught if the velocity is very much less than the speed of light. And suppose the speed does become equal to the speed of light, then v by c becomes 1. 1 minus 1 is 0. M naught upon 0 means infinite. So if a body starts to travel with the speed of light, its mass goes to infinity. Its mass becomes infinite if it is exactly equal to the speed of light. Now, we can say that this expression, that change in momentum is the change in the product of mass into velocity, is always correct. By definition, P is equal to mv by definition. So delta P will be delta mv by definition. It is always correct. But if you want to say that delta P is m delta V, that is only correct if V is very much smaller compared to C. Let me explain. Delta P is always delta mv. Mass and velocity both are variables. So first function into the change in the second plus second function into the change of the first, right? This is the complete expression for the change in momentum. This is always correct. But if you want to say that it is only delta P is equal to m delta V, if you want to say this, then the second term should be zero. That means m should be constant, delta m should be zero. That means the speed of the body should be very small compared to the speed of light. That means F equal to ma is only correct when the mass is constant. That means if the speed is of the body is very much less compared to the speed of light. So F equal to ma is a very special formulation of Newton's second law. The real formulation of second law is F equal to delta P by delta T, and delta P is m delta V plus V delta M. Remember that. So if you were to plot mass versus the speed, right? Mass of a body versus the speed. If the speed is zero, then the mass of the body is equal to the rest mass. As you increase the speed, the mass doesn't change, stays constant. Say at 1% of the speed of light, nothing happens. But when you approach 10% of the speed of light, that is when it becomes prominent and the mass begins to increase. And when the speed becomes equal to the speed of light, then it is tending to infinity. The mass is tending to infinity. That is the expression that we have for the relativistic mass. If you plot momentum versus velocity, momentum is mv, right? If the speed is small, less than 10% of the speed of light, then mass remains constant, speed is increasing. So momentum will increase along with the speed, right? Okay, linearly. But after that, when the speed exceeds zero point 0.1 c, then the mass itself begins to increase. And therefore, the momentum tends to infinity as the speed tends to the speed of light. So that's a kind of departure that you see from the normal behavior when the speed becomes extremely high. Okay, guys? So, talking of F equal to ma now, because in 95% of the cases, mass is constant. So that means in all those cases, F equal to ma will work. So rate of change of momentum, as you know, is delta P by delta T, which is delta mv by delta T always. What I mean by always is delta P is equal to delta mv always. However, in the case that the speed is very much less than compared to C, then delta P by delta T becomes, this numerator becomes m delta V because V delta M is 0. Then we are left with m delta V by delta T, that is ma, right? So force is equal to delta P by delta T is equal to ma, that proportionality constant is equal to 1 by suitable choice of units. So if the mass is 1 kg and the acceleration is 1 meter per second square, then the force acting on it is 1 Newton. And you can see here that this is a vector equation, therefore the acceleration will happen in the direction of the force. Which force? Net force. There may be multiple forces acting on a body, right? But you can always add them up to come to some net force. The acceleration will be along the net force. Okay. Seen another way, suppose Vi is initial velocity, Vf is final velocity. Initial momentum is mvi, final momentum is mvf. Then delta P by delta T. Delta P is final minus initial, that is mvf minus mvi. We can take m common, Vf minus Vi by delta T. But what is this quantity? Vf minus Vi by delta T, that is change in velocity divided by change in time, that is acceleration. So therefore we get ma. right? Now, under F equal to ma, if you were to plot acceleration versus force, the mass is constant. Then, as you increase the force, acceleration will also increase linearly when the mass is constant. Suppose you increase the mass, you apply the same constant force at 10 newtons, and you increase the mass. First, you had a small marble, then make it a stone, then make it a bigger rock, then make it a bigger rock. So you keep on increasing the mass and you keep applying the same force, then the behavior will be what? The acceleration will drop like this. Why? Acceleration is force upon mass, right? Force is constant. If you increase the mass, then the acceleration will decrease, but not linearly, because when you plot this kind of a graph, it becomes a hyperbola. This will be a hyperbola curve. Whereas in this example, mass is constant. So if you write acceleration as F by m and mass is constant, you are increasing the force, then the acceleration will increase linearly along with the force. Okay. You see this rocket that is going, it is ejecting gases and its mass is changing. Suppose it is going with a constant velocity, the rocket. Suppose it is going with a constant velocity. Is its momentum constant? No, the mass is decreasing, so the momentum is decreasing. You can have a change of momentum due to a change in mass. But hang on, moment you are talking of change of momentum, that means there must be a force on it. Just think about it, guys, the scenario. I'm saying suppose a rocket is going with a constant velocity. It is ejecting gases, but it is going with a constant velocity. The mass is decreasing, momentum is decreasing. That means momentum is changing. If momentum is changing, there must be a force on it. From where is that force coming? You get the point, you get the question. So let's think. So suppose we are saying that the velocity is constant. It is rarely so, but let's assume then its momentum is decreasing with time, correct? So delta P is always delta mv, but this one delta mv is m delta v plus v delta m, right? But in this particular example, the velocity is constant, so delta v is zero. That means this term vanishes, so it is v delta m. Delta p is v delta m. Force on the rocket is delta p by delta t, always, that is as per the Newton's second law. But delta p in this case is v delta m by delta t. And delta m quantity is a negative quantity because mass is reducing. When something is reducing, then the change in it is a negative quantity because change is final minus initial, right? If the quantity is reducing, then the final value is less than the initial value. So final minus initial will be a negative quantity. So since the mass is reducing, the delta m is a negative quantity. So V delta m by delta t is also a negative quantity. That means the force is acting against the rocket's direction. So the mass is reducing and the force is negative, but the velocity of the rocket is still constant. Okay. We can verify F equal to delta P by delta T, that is delta mv by delta T, that is m delta V by delta T plus V delta m by delta T. This is zero in this particular case because we are saying that the velocity is constant, right? In higher classes, we are going to derive it is ejecting gases, so there is a force on it due to the ejecting of gases. So its velocity and acceleration, both of them change in a certain manner, and we will be deriving the expression for the velocity and acceleration in 11th standard, not in 9th standard. Right now, just be very clear that you can have a change in momentum purely because the mass is changing. Purely because the mass is changing. Because momentum is mass into velocity. Either you change the mass or you change the velocity, the momentum is changing. Correct. So, some examples of second law in action. When a fielder catches the ball, he doesn't keep his hand like this. Come, 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 ball into my hand. If he just keeps his hand like this, it is definitely going to pop out. Definitely going to pop out. He pulls his hand towards himself, giving the ball greater time to stop. And if you're increasing the time, then the force exerted on the ball by the hand becomes lesser, thereby reducing the chances of the ball popping out of your hand. You must have seen how the catchers will catch the ball. You have a high jumper. After jumping, he lands on cushion. If the cushion is not there, he's going to injure himself. How does the cushion protect him from injury? Just like the example that we talk about, if you jump on a heap of sand, then you don't break your leg because the sand yields. It gives you additional time to stop. It lets your foot go into the sand. Similarly, cushion, when you hit the cushion with some speed, it will yield, it will bend, you can go down. Slowly, slowly you'll be stopping. And therefore the force on you is much smaller. And hence you don't break, you don't have an injury. If you have a glass and you drop it on your concrete floor, it will break. But if it falls on a carpet, it won't break. Most likely it won't break. Same thing, carpet also yields, applying lesser force on the glass, therefore it doesn't break. Now, there's an important relationship that we want to arrive at between momentum and a quantity called kinetic energy. There'll be a later chapter when you're going to discuss work and energy, but right now I do want to introduce to you the concept of energy. Energy is the ability to exert a force. Energy is the ability to exert a force. And if you are able to exert a force, then you can do what is called work. So in textbooks, you will find energy is the capacity to do work. What is work? We will see in that particular chapter. Now, there is a form of energy called kinetic energy, which is by virtue of its motion. And the expression for kinetic energy is half mv square, where m is the mass and v is the speed. There is a relationship between kinetic energy and momentum. Momentum is a vector, kinetic energy is a scalar. Kinetic energy is half mv square. If I multiply and divide with m, suppose this quantity I multiply and divide by m, then the numerator becomes m square v square, and I have an m in the denominator. M square v square is mv whole square, that means p square. So we have a very important relationship that k is equal to p square by 2m. Please make a note of this. For a single body, that is important. Don't apply it for multiple bodies. I'll tell you why. It is only for a single body. K is equal to p square by 2m. K is a scalar quantity and p is a vector, but when you do p square, then it is just a scalar number. Let us do this question. Suppose a truck and a scooter have same kinetic energy. Whose speed is higher? So let me equate the kinetic energies. Half m of the truck velocity of the truck square, that is the speed of the truck square, is the kinetic energy of the truck, which is supposed to be equal to the kinetic energy of the scooter. So half mass of scooter into the speed of scooter square. Half cancels. So let me bring Vt square this side and let me take ms that side. Mt by ms. Well, mass of the truck is much larger than the mass of the scooter, right? So the left-hand side, this left-hand side quantity is very much greater than 1. That means Vs square by Vt square is very much greater than 1. That means Vs is very much greater than Vt. So the scooter has got a higher speed. Same kinetic energy, the scooter will have the higher speed. But who has got the larger momentum? If k is equal to p squared by 2m and they both have the same ke, then the momentum is proportional to square of the mass, right? If ke is the same as given in the question, then p square is equal to 2m into k. 2 is a constant, k is a constant in this particular example. That means p is proportional to square root of the mass. That means larger the mass, larger the momentum. So the momentum possessed by the truck is larger than that of the scooter. Amazing. The scooter has got the greater speed, but truck has got the larger momentum if both of them have the same kinetic energy. Finally, if I talk of a system of more than one bodies, consider a system of two masses. Suppose it is given that the magnitude of the momentum of the whole system is zero. Can we conclude that the kinetic energy of the system is also zero? Now, kinetic energy is a scalar. Suppose there is a system of many bodies, then the kinetic energy of the whole system will be simply the sum of the kinetic energy of body 1 plus body 2 plus body 3 plus body 4, etc. Right? If you say the kinetic energy of the system is zero, then it can only mean that all bodies are at rest. But is it? Not necessarily here. See, I can always have a scenario that I have two identical masses m going with identical speeds but in opposite directions. The momentum of this guy is mv, the momentum of this guy is minus mv because the velocity is pointing to the left. If I add the two momentums, the momentum of the system is a null vector, zero. The magnitude of the momentum of the system is zero. But clearly, the kinetic energy of the system is not zero because clearly both the bodies have a certain speed. Kinetic energy depends on speed, not on the direction of the speed. It doesn't depend on the velocity, it depends on the speed. Therefore, be very careful. If you said, oh, k is equal to p squared by 2m, p is zero, so k should be zero. That is applicable only for a single body. When you talk of multiple bodies, because of the fact that momentum is a vector and kinetic energy is a scalar, it becomes a lot more tricky. So don't jump to conclusions. Correct? So that was second law, and that is a primary law actually. From here, we will go on to the third law in the next lecture.